Thanks for the introduction. I'll try to keep myself short regarding people are already going towards the lunch. So starting with the problem description, I try to give some statistical intervals for the residual lifetime assessment due to fatigue rate growth. And well, that's basically the idea that we start with. We wanted to get correct initiation lines and fatigue and end of lifetime curves in SN curves. And of course, you see a pronounced statistical letter here. And the idea is now that this colleague that the work that my colleague Stefan Kulic has done and will present tomorrow to have specimens with two types of notch, one rather mild and one rather sharp notch, cycle them and observe the electric potential and measure the fatigue crack initiation and subsequent crack growth. As you see here, it's quite complicated task to conduct those experiments and especially to evaluate them to detect the point of crack initiation. Well, that's the stuff that Stefan will tell you tomorrow. Here comes the idea of this talk today, that is, we can of course calculate rather precisely the crack growth regime, especially if we start at the end point where we know the size of the crack upon fracture. And so we can do the vector calculation upon a certain point of crack initiation if we know the decrack behavior exactly. So that's why we were trying to get statistical intervals for those crack growth curves. We start with the threshold for long cracks. We are having a rather limited set of data points, 5 of them at 2 R ratios of -1 and 0.1. And of course you know for steels the intrinsic fatigue crack growth threshold at roughly 2.5 megapascal/millimeter. So what we can do here is a linear model for which we can get out the confidence intervals, as you have seen. With that, we can proceed to evaluate our crack growth measurements, which we have done at 3 different R ratios for a crack that should be fully open at the load ratio of 0.7, and then for the 2 load ratios of 0.1 and -1. What you see, and we can fit the parameters of Nastro equations, which is of course the constant C, the slope of the Paris region M, and the parameter P that controls the near threshold region. And of course also for that one we can get a statistical estimate of the parameters and the confidence intervals for those parameters. Now, regarding short cracks, because of course at the beginning the crack is short definition, we have to describe this behavior with the R curve, and we have now the colleague has augmented the Castro equation to deal with behavior of those short fatigue cracks. First, by modifying the threshold according to the R curve, and second by the factor F, which is also dependent now on the length of the fatigue crack. What we've used there is a empirical approach. We have approximated the R curve with sum of some exponential terms, giving the length case basically of crack closure, and we use the same exponential terms also for the factor F, just because it's of course the same mechanism that has to govern that one, and second, because we don't have any data to get a more sophisticated approach. So that's quite a hands-on approach. Still, we managed to get those parameters with the confidence limits, respectively with the coefficient of variation. And with that now we can do residual lifetime assessment. Of course, we have to take into account the plastic zone in front of the notch, which Stefan has assessed by means of finite element computations. And in this zone in front of the notch, we have residual stresses that change the load ratio that the crack tip feels. And of course, we have to account for the plastic stress field in the notch, which influences we have done via Neuber's geometry function for the crack growth in the notch. So, with all that, we get a prediction, which is the black curve with the mean values of our regression model. And it compares, well, not too bad with the experimental results, which you see here in those bright colors. The interesting thing is now that the experimental results are bounded quite well by plus and minus 1 coefficient of the variation of the parameter values of the crack growth operation. However, we have also some systematic over-prediction for smaller cracks and some systematic under-prediction for larger cracks, which is all the more pronounced if we go to the sharp notch. So here you see really smaller cracks grow slower than expected, longer cracks grow faster than expected, albeit always within those confidence limits. So it could be worse. Of course, it could be better. We have identified some points that we could be better, especially regarding the shape of the crack near the point of initiation, because clearly near the point of initiation it's not a straight crack front. All that you will hear if you go to Stefan's talk tomorrow. Now, the prediction of this scatter of the lifetime, we are still not very much further because we have that much scatter in the crack growth curves and only a couple of data points regarding lifetime. So the idea now was, if we don't have so many experiments, let's just do some statistical Monte Carlo simulations to conclude upon the scatter of the fatigue crack growth lifetime. And here we are rather at the beginning. What I did is I took this model, which at the moment is not yet included in the model, is the distribution of the residual stresses. So all has been done for a stress ratio, load ratio 0.1. But with the scatter of the parameters as we have seen it. And then I did 1,000 simulations, and every time I threw the dice and got each parameter of the Nastro equation, and then let the crack grow at the fraction of the specimen. And what we get is this empirical distribution, and of course we see that it is not a normal distribution due to its skewness. On the other hand, it's not a log normal and for sure not a dipole distribution either. The question is, which kind of distribution could it be? And for this purpose, well, here again you see that the distributions are quite far off. For this purpose, I did, by using the statistical package R, some bootstrap samples of those 1,000 numerical samples that I did. And what you see with the blue dot is the parameters of my empirical distribution of those 1,000 Monte Carlo simulations. And the plot is the kurtosis over the square skewness. And this, what we see here, basically is a characterization of the third and the fourth moments of the empirical distribution. And you see that this one is quite far off any of the known distributions. Of course, we also see, regarding the orange data points, which is scattered from the bootstrap samples, we see that lots more simulations will be necessary to get the real empirical distribution. But anyway, the message is, as we feel at the moment, the lifetime, at least the fatigue crack growth lifetime, cannot be approximated by any of the simple statistical distributions. We will have to do some more simulations to get the real empirical distribution as from simulations. But for sure, the classical assumptions as to being normal or a log normal distributions are probably not completely correct. Albeit is the best what we can do regarding the small number of tests that we normally have. So that's it. And for all the rest, especially regarding how we did the experiments and how the evaluation of the point of crack initiation was done and the influence of the crack shape in the very early stages of crack growth, I would just invite you to join Stefan tomorrow in his talk. Thank you.